Okay, so here we are going to talk about instruction pipeline, okay, in this lecture. And instruction pipeline means we will send one instruction, okay, from one side, and we'll be getting a completed instruction from the other side, okay. So that is what the instruction pipeline is, right? So now if you want to construct an M stage pipeline, we should able to divide the entire control unit, okay, this entire control unit, this is what control unit, into M functional units which are independent of each other, right? So previously I had already explained that whenever we are constructing a pipelining, okay, so every stage should have a buffer associated with it, right? Should have buffer associated with it. But I never told you what was the reason behind it, right? So here this is how the exact architect look like. So control unit is divided into, I told you, no, it will divide into functional unit. This is what I'm calling a functional unit. This entire thing I'm calling it a functional unit. So it will divide like this, like this, like this, and each division is called as stages, okay, or phases. So this entire part is called a stage 1, and this entire part is called a stage 2, this entire part is called stage 3, this entire part is called stage 4. And this is where I am calling it as, like for example, the stage 1 I can call it as instruction fetch, this instruction decode, execution phase, then what, write back. Like this I can go up to n stages, I can go up to m stages, okay, there is no restriction. So how many number of m stages are there, that much functional unit is required, okay. Now you can clearly see this functional unit is consist of what, a combination circuit, first is one combination circuit, and a register R1, right? So if we take one phase S1, if we take one phase S1, and this phase will contain certain combination circuit, that is C1, right? And before we give the data into a C1, before we give a data into C1, okay, we have to store it in a register R1, okay. That is that is the meaning of this particular functional unit. So before giving any data to C1, first you have to store that data inside a R1, right? And the output of the S1, that means this particular S1, whatever the output is going to be stored in the register or buffer of R2 associated with the next phase 2, okay. This is phase 2, that is S2, getting it? So whatever the output you get, it will be stored first inside this R2, okay, which this R2 is associated with this particular stage S2, okay. So I will write it, so you can consider this particular stage is S2, this is S3, this is S4, okay, this entire part, right? Fine, okay. Now still we have a query, right? Why we need this particular register or a buffer, right, at the functional unit. So to understand this, let add some delays to the registers, okay. So I'm going to add some delays to the register. For example, each register will take 1 nanoseconds, for example, okay. This is the delay I'm adding, 1 nanoseconds, right? And suppose combination circuit also add some delays, for example, that is 10 nanoseconds, okay. So we are adding even delays, okay, for every function unit. So we can see combinedly, when we combine this entire function unit, the total is how much? We can clearly see the total would be 11 nanoseconds everywhere. Every function unit is taking 11 nanoseconds. Every phase is taking 11 nanoseconds total, right? So what does it mean? That means if any data get inside this particular phase, okay, and then it has to take 11 nanoseconds to complete its process, okay, in that particular phase, okay. Then after that only it will move to the next phase, and after moving to the next phase, it will take again 11 nanoseconds to complete its particular process in that phase. Then it will move to the next phase, and here also it will take 11 nanoseconds, so on, like this. Okay, that is the meaning of this particular time period. Okay, now there is one more thing, that is something called clock. Okay, so this particular functional unit will take a delay of 11 nanoseconds to process the particular data, particular instruction. Okay, that is fine, but after processing, the instruction has to move to another phase, right? That particular instruction has to move to another phase, right? For that we need a timing signal. Okay, we know that all these phases will be managed by control unit, right? And control unit will give a timing signal or a control signal appropriately to see that the data will move between every phases. Okay, so after completing this process, data will not automatically move. You have to set the time period in such a way that at that particular time, okay, the data will move, and that timing has to be set in such a way that, you know, when that particular data is finished, particular instruction finishes execution in that particular phase, at that time only the timer should be set in such a way that data will move to the next phase. Okay, what I mean is, for example, there is some clock signal, right? For example, there is one clock signal, we already seen it. Then what would be the time period for this clock signal? Okay, so this particular phase will take 11 nanoseconds, right? Then this clock, after that process is over, you have to trigger a timer, you have to trigger a clock, then only data will move to the next phase. Okay, so that time period should be 11 nanoseconds. We will set this time period to 11 nanoseconds. This entire thing is 11 nanoseconds. Then when this particular process, this function will complete its execution, then this clock will be triggered. Okay, at 11 nanosecond exactly this clock will be triggered and the data will be moved to next phase. Are you getting it? And then after coming to here, again it will process for 11 nanosecond, and exactly at 11 nanosecond the clock will be triggered and the data will be processed, passed to next phase. And here also the data will be processed for 11 nanoseconds, and exactly at 11 nanoseconds this clock will be triggered and the data will move to next phase, right? And here also same thing. Okay, that is why the timing signal is required. Okay, see, without this clock the data will not move. Okay, to move the data you need a clock signal. That is how our control unit works. Okay, because clock signal gives the one. In one of the lecture also I explained about the when you want to move the data from register A to B, you have to give a clock signal of positive edges, right? So when this positive edge came, then at that time only this data will move to another register. The same thing is happening. Okay, so clock has to be set in such a way. Okay, this is fine, but still that query is there, why we need a register still, right? Now I will take one more scenario, you will understand then why we need a register, right? Still that question is there, right? Okay, now we will take one more scenario. In that what we will do, we will assign, see here we can see there are all even delays, right? All the delays are same in all the functional unit. Okay, so in spite of that what I will do is I will assign a uneven delays. Okay, so I will remove this part, I will assign uneven delays in the combination circuit. Okay, then you will see there would be one problem here, right? Okay, so you can clearly see I had put uneven delay for the combination circuit. I put a 9 nanosecond C1. For C2 I had put combination circuit C2 11 nanosecond. Like this all the delays are uneven. So together what would be the answer then? Now everything will be changed, right? Right. Now what would be the answer here? This will be 10 nanoseconds, this functional unit. The delay for this functional unit will be 12 nanoseconds, right? Delay for this function unit will be 13 nanoseconds and delay for this function unit will be 14 nanoseconds. right? Now you will observe one problem here. Okay, to understand this, suppose assume that at phase 2 I1 is processing. Okay, suppose at phase 2 I1 is processing, and at phase 1, that means stage 1, I2 is processing. Okay, just assume this, right? Now I have to set a clock time period also, right? Right. Now let observe what would be the problem. Now my question is, what would be the time period? See, back then, what time period should I set now? Means what would be the clock signal? See, why we see again, try to understand why we need a clock. Whenever we enable the clock, then only the particular data will move from one functional unit to another functional unit, or one register to another function register. Okay, so whenever we enable the clock, then only it will move, otherwise it will not move. And this particular uh, time delay is for this particular phase to complete its execution. Okay, and after that time signal, okay, according to the time signal, okay, whatever the time you had set, then it will, that particular clock, the clock will be enabled, and that particular data will be moved. Okay, now my question is, what would be the time period? Okay, so you tell me, if I, because there is uneven delay. Back then it was even delay, so every phases was taking 11 nanoseconds, but here there are uneven delay, right? So for uneven delay, what would be the timing signal? What would be the time period? So suppose you will say that try to fix the clock using a smallest required time. So you will try to take the smallest time period, that is 10 nanoseconds. So I will try to set the clock with 10 nanoseconds. For example, I will take time period as 10 nanoseconds. So this will be 10 nanoseconds. That means after 10 nanoseconds, clock will be enabled and you can move the data from one function unit to another function unit. Okay, now let's observe what will happen then in this scenario. Okay, so now you can see that I2 is processing at phase 1 and I1 is processing in phase 2. Right, now after 10 nanosecond, I2 will complete its processing at phase 1, right? Then after 10 nanosecond, time clock will be enabled, right? Because 10 nanosecond is the time period, right? So clock will be enabled, and the data, that means this particular instruction I2 will be moved to the phase 2, right? But coming to here, at phase 2 takes 12 nanosecond to complete its process, right? Meanwhile, I1 is already reached to phase 2. Now there is an overlapping, because I2 has this phase 2 has not completed the process, and already I1 is came to the phase 2. Right, now there is an overlapping, and this creates a problem to a pipeline. Right, so how can you resolve it? So the answer is very simple. We will take the largest time period here. What are the largest time period here? Among them, 40 nanoseconds, and I will set the time period as 40 nanoseconds instead of smallest one. So now by setting this, all the problem will be solved. Okay, so I will take time period as 40 nanoseconds. Then what will happen? Let observe. Then again, I1 is at phase, I2 is at phase 1, right? It will complete its execution at 10 nanoseconds, right? I mean, it will complete its process at 10 nanoseconds at phase 1. Then after that, it will wait for 40 nanoseconds. Okay, because at 40 nanosecond clock will be enabled, then only that particular data will be moved. That means that particular instruction I1 will be moved, and meanwhile this phase has already completed its execution because it takes only 12 nanoseconds. Okay, so why 40 nanoseconds I1 will be moved to phase 2 and I2 will be moved to phase 2 and I1 will be moved to next phase, right? So this is how the synchronization will happen, right? This happened because we had set the time period to the largest time period. We had taken the time period to the largest time period possible. That is why this particular problem has solved. So whenever there is a pipelining, okay, and whenever there is an uneven delay, okay, and you have to set the time period, then take the largest time period possible. Okay, then it will resolve all the problem. Okay, fine. This is one concept you have to understand and is very important. Please note it down. Okay, now the next thing is, if the time period is 14 nanosecond, if I ask frequency, then what would be the frequency? Frequency is nothing but 1 by t. Then frequency will be 1 upon 40 nanoseconds. Okay, so this will be the frequency, right?